All right, so today we're going to wrap up our review of integration, and we're going to start chapter 7, which is the first new chapter for Calc 2, where we're going to be looking at physical applications of integration. But first, we want to go back and finish up our discussion about U substitution, which is what we were working on last time. There's a few more details we need to consider. So let's go back. And this is, by the way, as far as the slide numbers go, this is section 4.5, which is the last one. So we got about halfway through this section, and we did several examples with U substitution. But now here's the one thing we haven't done yet. All of these examples of U substitution asked us to solve for an indefinite integral. Okay, so what we haven't seen yet is how to handle the case of solving for a definite integral with U substitution. Okay, because it means we have to do something about the limits of integration. If we're going to use U instead of X, we do have to adjust the limits of integration. So we'll see how that works in a second. So first, let's look at an example. And so here we have x times x squared plus 1 cubed dx evaluated between 0 and 1. So this is a definite integral. Now, we already know how to do this with U substitution, right? So the basic steps are these. We start out by noting that we have a product here. This is a second degree polynomial. We're going to treat this as U. And here's our first degree polynomial. So when we combine that with dx, we may have du. So let's find out. So if we let u equal x squared plus 1, that means that du dx is 2x, or du equals 2x dx. So let's rewrite this a little bit. You can see we almost have what we need. This is definitely u. This is u cubed, actually. The problem is, in order to have du in our expression, we're going to need 2x dx, but we only have x dx. So here, it's a simple matter of supplying the missing constant. So what we're going to do is rewrite this as so you can see all we did here was simultaneously multiply this expression by 2 and multiply by a half, or divide by 2. So you haven't changed anything, but all of a sudden we have something in a much more convenient format, because you can see clearly that this is u cubed, and here we do have our du. So we can apply the so-called general power rule to come up with this. Now, if this was an indefinite integral, we would also add the constant of integration. But it is a definite integral, so we're not going to do that. The problem, though, is this. The 0 and the 1 refer to x, and we're dealing directly with u here. So what we're supposed to do here to make up for this is we're going to change these two. And what we're going to do is replace this 0. If u is, as we said, x squared plus 1, that implies that when x equals 0, that leaves us with a value 1 for x, and for the upper limit, we replace that x with 1, and we end up with an upper limit of integration of 2. Okay, so in other words, we should be integrating this over the interval not from 0 to 1, but from 1 to 2. All right, so then that means we have, and by the way, this is, remember we saw earlier that what we're doing here is a result of the second fundamental theorem of calculus. So this first term should be 2 to the 4 over 4 minus 1 to the 4th over 4. Notice there's no constant. We don't need it because this is a definite integral. Um, oh, what happened there? Yep, oh, I see. I just wrote it very badly. 1 to the 4th. Okay. All right. So in other words, this part we're very familiar with. Inside the brackets, we're going to have 2 to the 4th over 4 minus 1 to the 4th over 4. On the outside, we still have a half. Should be. All right. So that leaves us with 15 fourths. So ultimately, we end up with 15 eighths. That is the final answer. Now, if you're interested, I mean, we can draw this graph and take a look at it, but the final answer is 15 eighths. And so the key to the whole thing, and this is the new part, what you're supposed to do when you integrate is you can't just leave the limits of integration at the original levels if you're going to use u substitution. You have to change them to the values of u, in this case when x equals 0 and when x equals 1. Then you'll get the right answer. Okay, if you forget about that, of course you'll get the wrong answer. Okay, so that is the new part of this. Okay, and you can see that now actually here what they did was just to reinforce this, they changed it back, but once they replaced this with x plus 1, and this wasn't absolutely necessary. As you can see, we could have done it either way. You then would go back to the original limits of integration, and of course you'll end up with the same answer either way. Okay, you use the first approach, they're using the second approach, but you're still doing the same thing. So, all right, now that we know how that works, we're going to look at, by the way, even and odd functions. I think we may have mentioned this earlier in our reviews. What does it mean for a function to be even, and what does it mean to be odd? Let's just quickly run through that. First of all, not all functions are either even or odd. I mean, some of them are, and of course, no function can be both. So let's run through this rule. So the formal definition of an even function is so if for every x in the domain, f of x equals f of negative x, you have an even function. And the classic example of this would be y equals x squared. Okay, so in other words, if we look at a parabola, for example, f of 2 is 4. F of negative 2 is also 4. Okay. Now, of course, here we only are seeing one example of this, but we can prove that this is true for every x in the domain, which, by the way, the domain in this case is all real numbers. No matter what x we have, f of x is x squared, f of negative x is negative x squared, which of course will end up being simply x squared. So in other words, it doesn't matter what x we picked, we would get the same result. So therefore, we call this an even function. You can tell graphically just by looking at it, because there's going to be symmetry with respect to the vertical axis. In other words, although I didn't draw this very well, the left and the right-hand side with respect to the vertical axis will be mirror images of each other with an even function. Also, even functions are going to have a degree which is even, meaning that it could be squared, 4th power, 6th power, whatever. If you had something like y equals x cubed, it's not going to be an even function because the degree is not even. So now an odd function means that For every x in the domain, we have this result. Okay. Now, the classic example of this is y equals x cubed. So, for example, f of 2 is 8. F of negative 2 is negative 8. Okay. So if I choose x to be 2, because f of negative 2 is negative 8, and when we multiply that by negative 1, it becomes positive 8. And that's going to be true for all x's in the domain, which in this case, again, is all real numbers. So in other words, and they're the same. So that means that y equals x cubed is an odd function. And again, just like with the evens, the degree of this polynomial will tell me if it could at least be an odd or even function. So if the degree is odd, it could be an odd function. It doesn't have to be, but it could be. Okay, so it doesn't guarantee anything. Just because you have some function y equals x to the fifth, and then all the other terms will determine whether it is odd or even. But if you see that the degree is not odd, then the function can't be odd either. And so many functions, I shouldn't say most, many functions are neither odd nor even. All right, so with that being determined, how do you find the integral of an odd or an even function? So they're showing you a couple of graphs here. Now, in the first case, we have an even function, and you can tell because it's a parabola, which means it's a quadratic function. It's one that's facing down, but it's still even. And so you can see we might be interested in the area between negative and positive a. And there is some symmetry there. Now, this is the whole point of all this. This area equals this area. Once we know that it's an even function, we're guaranteed that there's symmetry with respect to the vertical axis, which means these two areas are equal to each other. So if I call this A and A, well, they're equal to each other. The total area is 2A. Now over here, oh, I forgot to mention one more thing about odd functions. With an even function, I guess I didn't write it in here. I'll summarize this at the bottom. With an even function, the graph is symmetrical with respect to the vertical axis or the y-axis. Now, interestingly enough, with an odd function, the graph is symmetrical with respect to the origin. Now, that seems a little strange. That means that there's a couple of possibilities. Either the function is identical in the first and the third quadrants, or in the second and fourth quadrants. So, for example, you visualize that in this case, if you took that first quadrant and flipped it over into the third quadrant, you can see that they're identical to each other. So the symmetry is with respect to the origin in this case. That also means that this area down here is the same as this, except one is positive and one is negative. So anyway, that's the logic behind what's going to happen here. These numbers, this you can think of this as a and negative a. Let's put it that way. So if I combine them directly the way they're written, I'll always get zero. On the left-hand side, if I combine them, I will always end up with 2a. Okay, so that's what this is all about, what we're about to do. Anyway, here we go. So if we have an even function, and this is exactly what we're just seeing, evaluated over the interval from negative to positive a, what we could do is treat it as 2 times the area to the right of the vertical axis. Okay, in other words, if you notice the lower and upper limits, instead of negative a and positive a, it's from 0 up to a. So what they're saying is you can just double this piece here because of the symmetry. This one, though, as we just discussed, because it's odd, and you're going to have some of the function will be above the horizontal axis and some would be below, and they're equal to each other. One is negative and one is positive. If we add them directly to each other, we have to end up with 0. Okay. So the total area between negative a and a plus negative a, 0. Okay, here are the total areas to it. All right, so we're going to try an example here. Now, this is a tricky one to prove if it's odd or even, but there are rules. I don't know if we have a table. There exists, I know there's a table floating around out there somewhere, which shows, if I'm remembering correctly, 4 of the trig functions are odd and 2 of them are even. I'll see what I can do about getting my hands on that list. But, oh, if we can probably find it on the internet. Which trig functions are even, which are there, yeah, there it is. All right. I'm gonna borrow this. I guess anything on the internet, I guess I could feel free to copy it into my notes here. As long as I look at all those ads. Yeah, I'll update Snagit later on. Okay. And they're also explaining to us why this is happening. Yeah, sometimes it works well, sometimes it's very slow. All right, when that happens, I just try it again. It usually does the job. And it's really being stubborn today. Um, it would have been quicker to just write this down. This is just unbelievable. It has its moments. It's like all technology. It works when it feels like working. All right, let me just quickly write these down. I can see where it's just, oh, all right, finally. All right, here we go. So yes, of all the 6, basic trig functions. Four of them are odd. And the reason is right here. This is what we were just discussing. And the even ones are over here on the left. So here they're giving us now this is a tricky one. It would be very time consuming, I think, to prove that this is either even or odd. But all right, well, they're telling us that it's odd. And you could double check by trying different values of x. But anyway, so the interval is between positive and negative pi over 2, which is 90 degrees. Wow, this is a tricky function. You know, I'll tell you what, why don't we draw a picture of it in Lab, just so we can visualize what's happening here. All right, look at this. Y equals sine cubed x cosine x plus sine x cosine x. All right, so let's take a look at this graph. Just thinking. Like I said, the technology works. It feels like working. All right, we don't need this. Let's just go ahead and evaluate it. So the interval is between negative and positive pi over 2. Oh, here it is. Okay. So what they want us to do is figure out the area here. And because this is an odd function, this is going to give us an odd value. Oh, okay. I guess they didn't mean for us to work it all the way through because it is a very messy function. But here I think they do want us to evaluate it. These are indefinite integrals. All right, well, we'll give these a shot. Oh, I see. It's a multiple choice question. All right, let's try this one. This will give us some more practice with U substitution. I guess we're not going to use this one. So what do we? Oh, let me just copy this. Now, of course, remember, you're always looking for the highest degree. When you have polynomials like this, you always look for the one with the highest degree. That is usually going to be your U. In this case, it's du dt, actually. The constant, of course, has a derivative of 0. So do we actually have that? No, but we're close. You can see we're missing the 5. We just have to supply a 5 and we'll be all set. So we'll multiply by 1/5. And here that leaves us with 5t to the 4th. Okay, this is our du. This means we have u cubed. And so we ultimately end up with 1/5 to the 4th over 4 plus c, because this one is an indefinite integral. And of course, u itself is equal to t to the fifth plus 4. All right. So it's obviously B. All right. Oh, they got a few more challenges for us here. Okay, well, this is the last one. Let's take a look at it. Now, these are a little bit different because these are trig functions. So you got to remember the way these work. Uh, we're definitely going to need that chart for the derivatives of the basic trig functions. Um, There it is. Okay, great. So that will help us decide what to do about u in this case. Now, in a case like this, it could be easy to get confused, but if you notice that even though these are not polynomials, cosine cubed has a higher degree. Okay, so chances are that's going to be the u in our substitution. And like I said the other day, if we guess wrong, well then, it'll become clear very quickly and we can just try something different. So I think what we should do is let e be the cosine of x. And of course, based on our chart, that means we have negative sine x as our derivative. Just one. Okay. Oh, and by the way, if you notice here, we're missing a negative. Right. So in other words, if you look at this carefully, this could be rewritten as a negative. We can supply that ourselves because it's equivalent to multiplying and dividing by -1. And so we're all set because what do we have here? We've got 1 over u cubed. Oh, sorry, I must have missed a negative. That would have been bad. Negative 1 over u cubed du. Now, I think it would be easier to write like this. We can apply the general power rule. And we end up with negative u to the -2 or -2. Or if you prefer, you can write it as 1 over 2 squared. And since u is the cosine, and of course, because there's so many trig identities, there are other ways we could write this, but we end up here with 1 over 2 cosine squared x. Let's see. So it looks like A is our answer. Yes. Okay. So, you have plenty of practice with this u substitution. Actually, I'm not sure if you'll have to do any of those in WebAssign because the WebAssign is only doing the Calculus 1 problems. So, but they'll show up again later on in Chapter 8. So, but anyway, in the meantime, we're ready for Chapter 7, which is the very beginning of this course, actually. But you'll see right away, it's just like it's like the sequel to a novel. Basically, you're just going on from where we left off in Calc 1. It's not different. We're just focusing on different concepts. And So we're going to start here by reviewing different physical applications of integration. And so, for example, what they're going to do here is show us how we can now integrate between two points and come up with the area between not just a curve and the horizontal axis, but between two different curves. Okay, so this is the first time we've seen this. So what has to happen here is that you're going to have to subtract one integral from another. Okay, so in other words, if you let me make this a little bit bigger. No, that's better. Okay, so now if you notice, they're only interested in the area between A and B. So within that interval, F is always, in this case, always above G. So they're trying to help you see the difference by making the F is a very bold line and the G is a gray line. Um, so that being the case, if you notice, the integral that we need is not just the integral of f of x dx, which is what it would be if we were looking at the area between the curve and the axis. Because it's the area between f of x and g of x, we're subtracting one from the other. Um, oh, and yes, okay, this is what I was referring to before. Just this is what we were doing earlier. Um, we were just considering the area under that curve all the way down to the horizontal axis. So that is much more simple. It's simply the integral of f of x dx from a to b. Now here they're showing us that the area under G, as you can probably guess, based on the rest of this, is equal to everything, the integral from g of x down to the horizontal axis, which would be g of x dx. And so finally, what they're showing you here is that by taking the entire area and subtracting the area under G, what's left is the area between F and G. So in terms of geometry, it makes perfect sense. Okay, so you have two curves like this, as opposed to one curve in the axis, calculating definite integrals is a little bit different. All right, so now what they also are going, they're building up to a result that we'll need later on, but what they're saying is that within that distance between the two curves, we could partition this into a bunch of rectangles of with delta x. The height is simply the difference between f of x and g of x at that point xi. So let me copy this into my notes one more time so you can see it better. So what they're basically asking you to do is visualize that for each xi in this interval, there's a rectangle that represents the gap between the two curves. And so what they're going to do is put a series of these inside these two curves to come up with results that we need. We'll see what that leads to in a bit. But they're starting us out by showing us how this rectangle spans the gap between f of x and g of x. The width is defined as delta x. Okay, we choose that, by the way. And so what they'll show us is that in the limit, as these widths get smaller, which means there's more rectangles, we'll end up ultimately with the area between the two curves. All right, so where is this going? So as the delta gets closer to zero, meaning the number of rectangles gets very large, ultimately the area between the two curves is equal to or converges to the integral of f of x minus g of x between a and b. And so they're going to designate that a. So this is the general result. Let's see. Now these are a little bit different. So I guess here, what they want to see is that the location, in other words, the curves don't have to be above the horizontal axis. Um, like you can see here that F is above the axis, G is largely below. And over here on the right, in this case, both curves are actually below the horizontal axis. And so the results won't change. Still the same area. All right, here we go. Now, this is the first question for us. How do you find so by the way, here's the two functions. F of x is x squared plus 2. We have a quadratic function directly beneath it. We have a linear function g of x equals negative x. We're interested in the interval from 0 to 1. That tan region is what we're looking for. And the rectangle that we're seeing here, which they're calling it the representative rectangle, has a height equal to f of x, wherever x is. Actually, the height is the difference between f of x and g of x. All right, so what are we going to do with all this? So we get the region bounded by the graph f of x, g of x over the interval 0 to 1. So we're going to combine all of this, and we're going to take the integral based on what we've just seen over the interval from 0 to 1. So we're going to end with x squared plus 2 plus x dx. Now, of course, normally we will write it in descending order of the degree of each of these terms. So we'll rewrite it slightly as all right. So what do we end up with? So it's x cubed over 3 plus x squared over 2 plus 2x evaluated between 0 and 1. Okay. And then now that means we have to evaluate that function where x equals 1, then we do the same thing with 0. Okay, so then we combine these. So of course we're going to need a common denominator. Let's go with 6. All right, we don't need these zeros. Let's get that out. And we end up with 17 over 6. Okay, so this is a very simple extension of what we were doing in the previous chapter. The difference being now that we have two curves instead of one curve and the axis. The process hasn't changed. Okay, so now we're going to look at a slightly different example. And what's different between the case we just saw and this one is that in this case, the two curves actually intersect each other, or at least they intersect within the interval of interest. So back here, in this case that we just looked at, these two curves never obviously crossed. So let's go back to our notes and revisit this for a second. And you can see they did not ever actually cross within the interval from 0 to 1 that we were interested in. Here they do. Okay, so the only real difference here is that we do need to know where they do cross and use those as our limits of integration. So just from the curves themselves, you can see, just visually, you can see where they cross. But why don't we prove this algebraically by setting them equal to each other? So we have the straight line, g of x equals x. And then we have this quadratic function, f of x equals 2 minus x squared. So where do they cross? Well, let's just set these equal to each other. Okay, solve. Now, of course, there's going to be 2 points because the result will be another quadratic expression. And now, in this case, it's such a simple result that we can factor it out. End up with 2 solutions, -2 and +1. Okay, so now what we're going to do, like we did before, is we're going to calculate the integral of the difference between the two over the interval from -2 to 1. But just be careful here. Within the interval of interest, um, make sure it is f of x, the bold-faced line or curve rather, that is on top. G of x, the straight line, is underneath. So we will solve for f of x minus g of x. Otherwise, we would reverse these. Okay, so let's plug in the formulas. So again, f of x is 2 minus x squared, and g of x is simply x. All right, so we'll simplify this a little bit. And now we'll integrate and evaluate it. All right. So now we solve for the 2 intervals of integration. In other words, we need to solve for this expression when x equals 1, and then we do the same thing for x equals -2, and then subtract. In other words, following along with the second fundamental theorem of calculus. See what we've got. Okay, so on the left-hand side, we have 2 minus a third minus a half. On the right-hand side, we have -4. So now -2 cubed is -8. This becomes +8. And then -2 squared is 4. So we have -4 halves. So we're going to obviously need some, we're going to need to find a common denominator for all these terms. Let's try sixths. Over here, we might as well do the same thing. That one's going to be 12 over 6. Okay. Oh, I just want to be a little careful. This starts to look like a 12 here. Let me just fix that. Be very careful when I write with this tablet. Okay, here we go. Oh, I just realized these are supposed to be sixths. Okay, let's try that again. Better. Okay. So inside the parentheses on the left, 12 minus 2, that gives us 7, 6. Over here, we have the area is 9/2. Okay. So yeah, that was a lot of work. Well, it wasn't that much work, but we have to be so careful. There's so many opportunities to make mistakes here. So anyway, but the area is 9/2 between the 2 points where the curves cross, -2 and +1. All right. Now it gets interesting. If you notice the way the curves are laid out, um, yeah, we're going to have to take a different approach here because if you look at this case, we've got, oh, now here's what they want you to notice. All right, if you look at this graph carefully, up to this point, we've seen these rectangles. And, obviously the coordinates are s, x, f of x. But when we have a case like this, what we're going to do here is we're going to essentially do the same thing, except with respect to the horizontal axis instead of the vertical axis. So what we're going to do is write these functions in terms of y. Okay, now we haven't seen this before. And only again, you can see from the curves why this is a good idea, because the curves, one is to the right of the other. And so the first function will be written as f of y equals y plus 1. Their function is 3 minus y squared. Okay, now what do we do? This time, instead of the top curve minus the bottom curve, it'll be the right curve minus the left curve. Okay, so in other words, what we're looking for is the integral of, in this case, g of y minus f of y with respect to y. And what about the limits? Good question. Okay, so you can see where they cross. Now they've already told us where they are. The 2 points where they cross are -1, -2, and 1. But remember, everything is being done with respect to y. So what we're going to do is integrate between -2 and 1. So you can see in others, we're turning everything on its ear here. We're looking at the difference between the one on the right and the one on the left instead of top minus bottom, and everything is being done with respect to y. Okay, so now we plug everything in. Now at this point, we're going to approach this the way we usually do. Let's write these down. G of y is 3 minus y squared. And then f of y is y plus 1. Now the rules of integration haven't changed. So here's what we'll have. Right? Oh, wait, sorry. No, that's better. Okay. So in other words, we're evaluating it and then we're gonna first we integrate, then we evaluate. Okay, great. Okay. So then we plug in the numbers that we have. And let's see what happens. Actually, you know what? I think just to make this a little bit simpler, I'm going to combine these terms first. That might make it a little bit quicker and easier. We'll have 3y minus y cubed over 3 minus y squared over 2 minus y. Yeah, that might make it a little bit simpler. So then we can evaluate this where y equals 1. All right. So let's see what we get. Yes, sometimes the eraser just doesn't like to work. I just wanted to neaten it up a little bit. Here we go. Okay. So again, we'll be looking for a common denominator. We might as well use 6. Should 36 Okay. So the first one expression is